Hi everyone. Let's go ahead and get back to this bivariate distribution stuff we were talking about. Before I do that, I want you to, or I want to remind you that tomorrow I'll send out a homework quiz for you to work through. It will be basically a 48-hour turnover. So I'll send that out probably tomorrow afternoon or something, and you'll have basically 48 hours to upload that into Canvas. Okay, so you have the homework lists, you know what problems we've covered in your respective chapters. So hopefully that'll work out fine for you. Just please let me know if you run into any troubles or have any questions or anything. Okay, continuing to keep office hours and class time Zoom hours, so you can always get your questions answered there for sure. Okay. So I wanted to first return to this notion of covariance, which leads us into correlation, because this is extremely important, okay? I think that this is a topic that gets short shrift overall, so I just want to make sure that we're all on the same page here. First of all, last time I kind of skipped over the computation that I now want to actually revisit, and that's the following. So so first of all, what we do is we look at the product of x compared with its mean times y compared with its mean. Take the difference between those two. And what I said was, if x on average, okay, so suppose that this covariance ends up being positive. Well, that means that if x is above its mean, then y is tending to do so as well, so as to make that product positive. And similarly, if x is below its mean, then y is tending to be there as well, so as to have a negative times a negative being positive. Okay, because the overall covariance was positive. X and y are tending to reside on the same side of their respective means. So that means if x is small, y is small. And if x is large, y is large. Okay, so that's what's going on if the covariance is positive. But again, this is only measuring a linear relationship. Linear, okay? Other kinds of relationships like quadratic or exponential or logarithmic, whatever it is between x and y, that is not measured by this quantity, okay? On the other hand, if the covariance is negative, what that means is that if x resides above its mean, then y is tending to reside below and vice versa, so as to make that product negative on average, okay? So that's what's going on. I just want to remind you of that. And quickly, I wanted to actually write out this computation in full detail just so you could see it. I'm going to do that right here. So this thing is equal to the expected value. Let's multiply this out. This would be xy minus ux y, okay, minus uy x plus mu x mu y, right? Okay. So, and if I were to use the linearity of expectation and the fact that mu of x and mu of y are constants after all, in the end, this ends up being the expected value of xy minus mu x times the expected value of y, okay, minus mu y times the expected value of x, plus, okay, what's the expected value of mu x mu y? Well, that's a constant, okay, so that's just going to be mu x mu y, okay. And let's not horse around here. This expected value of x thing, that is just mu x. And what about this expected value of y thing? Well, that's just mu y, okay? So if you look at this overall, let me just kind of come down here. This is the expected value of xy. How many? I have minus 2 mu x mu y's, and then plus a mu x mu y. So this is minus 2 of these. So I mean, after all, let me just kind of write this. I'll take a blue color here. I mean, look at this. Just one of these things is canceling this guy right here. So it's just going to be minus mu x mu y. And that indeed is exactly what's written right there, okay? Ux is just the expected value of x, mu y is the expected value of y, okay? So I just wanted to, I just wanted to kind of write that out in full detail. It's worthwhile, okay? All right, so moving on. Once again, what we do is we kind of realize that, depending on what the units are of x and y. By the way, x could be dollars, and y could be cents or something like that. Okay? They're both acting on the same sample space, just extracting different quantities. So x could be dollars and y could be cents. And if I multiply those things together in the formula for the covariance, I could have units that they don't necessarily have to be squared. It could be dollar cents, dollar cents, okay? Dollars multiplied by cents. And that's just kind of weird. I mean, what does that even mean, okay? So what we do is we scale the covariance. We scale the covariance by the standard deviations of both, right? And remember, the standard deviation of x is going to have the same units as x, right? So if the covariance of xy was dollar cents, then sigma of x would have units of dollars, and sigma of y would have units of cents. So it would be dollar cents down below. And the units would cancel, and this thing here would be unitless. Unitless, okay? That's a unitless quantity, okay? This thing's kind of been standardized, and we kind of realized that we call this thing the correlation coefficient, or just the correlation for short, okay? Or we use CORR of x and y, or rho sub xy, or just rho, if you will. Okay, that's the Greek letter rho. Okay, rho. That's the Greek letter rho. Okay, and it turns out that that quantity, you can prove this mathematically. The quantity is always between -1 and 1. And so in the most extreme negative case, you would end up at -1, and in the most extreme positive case, you would be at +1. So, and if rho of x, y is equal to -1, this means perfect negative correlation. So that also means that it's going to be a perfect negative. Remember, correlation means linear relationship. Okay, so it's a perfect negative linear relationship. And what if rho sub xy is +1? Well, that's a perfect positive correlation. That's perfect positive correlation, which means that we have a perfect positive linear relationship. So what that means is that there is a line with a positive slope that defines the relationship between x and y. If you want to know what y is, plug x, based on what x is, just plug x into the line describing the relationship between x and y. They have a perfect positive linear relationship if rho sub xy is +1. Okay, so I mean, if it's positive, you're still going to have a somewhat slightly positive linear relationship, but it just won't lie necessarily on a perfectly straight line. Okay. Sometimes you will see things like in a scatter plot, and you'll have things like a trend line, and the degree to which that trend line actually stays close to the data is the degree to which we have correlation. Okay. All right. Moving on. So again, covariance depends on the units of measurement, right? So I already kind of talked about this. If two variables x and y are independent, then what's going to happen back here is the expected value of x, y, right? If x and y are independent, right? If x and y are independent, that implies that the expected value of x, y is equal to the expected value of x, expected value of y. And so if that happens, then of course the covariance would be 0. Okay, so that's what this is. That's what this is saying over here. Okay, X and Y are independent, the covariance is 0, and therefore the correlation coefficient is 0, but you cannot say that it goes in the opposite direction. One thing that I said I would show you is, well, you know, suppose that Y is equal to X squared. Clearly those things are related, okay? And suppose that X belongs to you know, -1, 0, and 1, okay? And the P of X, right, the probability of being equal to any one of these is just always a third, okay? It's always a third. So, so what would be like the expected value? What would be the expected value of X? Okay, well, it would be a third times -1 plus a third times 0 plus a third times 1. Excuse me, that would be 0. Okay, what about the expected value of Y? Okay, what about the expected value of Y? Well, the expected value of Y, now think about it, since Y is equal to X squared, Y belongs to 0, 1. That's it. And what is the probability for Y of being 0, right? This was the probability for X. What was the probability for Y of being 0? Well, that happens whenever X is 0, which happens with probability 1/3. And on the other hand, the probability for Y of being equal to 1, that happens whenever X is equal to either plus or minus 1. And so that happens with probability 2/3. 2/3, okay? So what's going on here? The expectation of Y is just equal to 1/3 times 0 plus 2/3 times 1. So the expected value of Y is actually 2/3. Okay. What about the expected value of XY? Okay, the expected value of XY. Well, again, you know, what is that going to be in this particular case? The expected value of XY, well, Y is equal to X squared. So this is just the expected value of X, okay, that's the expected value of, well, let's see here. Let me erase this, sorry. Erase that, okay. Go back in here. What is the expected value of XY? Well, what are the possible outcomes that we could have here? Well, Y could be 0 and X could be 0. Okay, so Y could be 0 and X could be 0. And that happens precisely if, so how often does that happen? That happens precisely if X is equal to 0. The only time that Y is 0 is when X is 0. So what is the probability that that happens? Well, 1/3. Okay, so let's take a look at that. So this is, you know, 0 times 0 times a third, because that's how often that happens. Okay, and then what else do we have here? You know, what is it if I get -1 times, right? If X is -1, Y is 1, right? So how often does that happen? Well, that happens with probability 1/3. Okay, and what about what if X is 1? Well, then Y is obviously 1, and how often does that happen? Well, that happens with probability 1/3. So what do I get? What do I get here? Hang on a second. What do I get here? So this should be 1/3. Let me get rid of this. 1/3. Something's wrong with my, oops. 1/3. There we go. And so this is going to be 0. Okay. So look, the expected value of XY is 0. Expected value of X is 0. The expected value of Y is 0. So what about the covariance? Think about it. The covariance of XY in this case is equal to 0, because the expected value of XY is 0. Expected value of X is 0. Expected value of Y is 0. So if we plug into the formula, we get 0. And yet, right, so but X and Y are dependent. Okay. So clearly, I mean, in the worst possible way. Y is actually a function of X in this particular case. Okay, so we have dependence in X and Y, even though the covariance is 0. That's why the implication can't be reversed. So that's one thing I wanted to point out. I just wanted to kind of close the loop from last time on that one. Okay, so let's move on from that. Go on to the next thing. So hang on a second, what's going on here? Go. So let me pause this for a second. Let's move on here. Okay, so let X be a random variable with probability mass function equal to that. Find the covariance of X and Y and the correlation coefficient, and decide if X and Y are independent if that happens. Let's just deal with A, right? So, so I mean, look at this. What would you expect to happen in A? Think about it. Y is a linear function of X, and it has a positive slope. So before we even start, we would expect to have a perfect positive linear relationship, i.e. perfect positive correlation, okay? Let's take a look at that and see if that's actually true here. So first of all, what is the probability? So like what are the possibilities for X? X could be 1 with probability 20%, 2 with probability 50%, and 3 with probability 30%. Okay, so let's go through that. So what about the expected value? What about the expected value of X? What is the expected value of X? Well, that's going to be equal to 1 times 0.2, okay, plus 2 times 0.5 plus 3 times 0.3. Okay, so the expected value of X is equal to 0.2 plus 1 plus what? Plus 0.9. Okay, 0.9. What's that equal to? Well, that's 2.1, all right? Okay, 2.1. Okay, and what about the expected value of Y? Well, that's pretty easy. You just plug in what Y is in terms of X, so that's 3X. Okay, and so what do we, if we just pull out the 3, okay, because after all the expectation is linear, it's going to be 3 times the previous guy, right? So 3 times the expected value of X, 3 times the expected value of X, and we end up getting 6.3, okay? Now, what about the expected value? So 6.3. Okay, so that thing looks like a multiplication symbol, but that's a decimal point. Okay, what about the expected value of XY? Well, Y is equal to 3X, all right? Y is equal to 3X. So, I mean, I can factor out the 3, and I'm going to just get that this is the expected value of X times X, which is X squared, basically. Okay, so what are we going to end up with here? So this is 3 times, okay, so let's see. What are the possibilities for X squared? Well, X squared could be 1 with probability 0.2 plus, okay, if X is equal to 2, which happens with probability 1/2, 2 squared is 4, okay, and that's going to happen 50% of the time. And X is 3 with probability 30%. If I square that, I get 9. I multiply that by 0.3. Okay, so what do we get? Well, this is 3 times what? So 4 times 1/2 is 2. So let me see. So this is 0.2 plus 2 plus 2.7. Okay. 2.7. Okay, so that's basically 2.9. Let's go up here a little bit. So 2.9 plus 2 more is 3 times 4.9. 3 times 4.9. Isn't that right? It's 4.7, 4.9. Okay, so 3 times 4.9. So what is that? Well, that's like 14.7. Okay, 14.7. Okay, so that's interesting. Okay, so what do we have? Let's kind of write these things down up here. I have the expected value of x is equal to 2.1. I have the expected value of y equaling 6.3. Okay, and I have the expected value of xy equaling what? Equaling 14.7. Okay, so what is the covariance of xy? Okay, what is the covariance of xy? Well, it's going to be 14.7 minus this product, 2.1 times 6.3, okay? Which is, let's see here, 14.7 minus 2.1 times 6.3. It's 1.47. Okay, so that's 1.47. Okay, and what about the individual standard deviations? Okay, what about the individual standard deviations? First of all, if I could compute the expected value of x, by the way, like look right here, 4.9. What was that? 4.9 was really, that was like the expected value of x squared, wasn't it? And that's what 4.9 was, if you kind of stare at what it is that we did there for a minute. Okay, so let's think about that for a minute, because I think that tells us what the variance of x is. Okay, so the variance of x is going to be equal to the expected value of x squared, which is 4.9, minus the expected value of x, which is 2.1 quantity squared. Yes, so let's see, that's what the variance of x is. So I go 4.9 minus 2.1 squared, okay, and I get 0.49, okay, which is pretty convenient. And that tells me, since that's the variance, I know that sigma sub x, let me write this over here, sigma sub x is going to be the square root of that, okay, the square root of 0.49, okay, and that works out nicely because I know what the square root of that is. That's just 0.7. And what about sigma sub y? Well, for that, I mean, look, the variance of y is just the variance of 3x when you think about it. Okay, and you know what's going to happen. That's going to be 9 times the variance of x. Okay, 9 times the variance of x. Okay, so that when I take the square root, right, so this guy, right, that's what y is right there. Okay, so when I take the square root of that, okay, so sigma sub y is going to be the square root of that. It's just going to be the square root of 9 times the square root of 0.49. Square root of 9 is 3, okay? So it's going to be 3 times 0.7. So I get 2.1, okay? I get 2.1. Okay, 2.1. Okay, so what is the correlation coefficient here? Okay, so let me just write this down here. Sigma sub xy. What is that going to be? Well, that's the covariance over the product of these two things, right? That's the covariance over the product of these two things. So it's going to be 1.47, okay, over the product of these two things, okay? 0.7, I'm just going to go ahead and multiply those things together. 2.1 times 0.7. And lo and behold, guess what that is? 1.47, which is 1. Okay, which should be no surprise to us. These things right here are in a positive linear relationship with one another, right? So we would expect perfect positive correlation here. Okay, and again, where did I get this guy right here? So the covariance is what's upstairs, and this guy down here, this 1.47 thing, that's just 2.1 times 0.7. Okay, because I multiplied the standard deviations together. Okay, so that's that. Moving on. And let's talk about conditional distributions. Okay, conditional distributions are basically the idea here is that we know what the value of one of the random variables is. Okay, so we know what the value of one of the random variables actually is. Okay. That's going to take us in a certain direction. So let's take a peek at this. Okay, so X and Y are just two continuous random variables with joint probability density P of XY, marginal densities P sub X of X and P sub Y of little y. Then given any X such that the marginal is positive, okay, and that's important because we're going to condition on big X being equal to little x, right? So we don't want to condition on an impossible event here. So look at that crazy notation. P sub y given x, and those are both capital letters, okay, is of y given little x, okay, is equal to P of xy divided by the probability that that big X is equal to little x, okay? And this kind of makes sense because if you think about it, what's upstairs? This is really like the probability that X is equal to little x and Y is equal to little y. And what's on the bottom? Well, that's basically like the probability that X is equal to little x. So, I mean, it's just like what we've done with conditional probability before. We know that we're now on the event that X, capital X, is equal to little x. And now we need to compute the probability of Y given that new information. So we've zoomed into the sample space to the place where capital X equals little x. We're just right on that. That's our new sample space. So that's why we divide by the probability that X is equal to little x. Now that's the part of the sample space we're on. And whatever the probability of big Y being equal to little y was before, we now need to say, okay, we no longer can look at all outcomes where that happens. We need to look at only those where X is equal to little x. So what we've done, I mean, here's kind of the generic picture right here. We're in the sample space, okay? So here's the event. Here's like the event X equals little x. Here's the event Y equals little y. Okay, and what we have now done, okay, is we've said that we are now, this is our new sample space right here. Probability that X is equal to little x. So I'm no longer allowed to be looking over here, right? That is right. So no, I can't be right there anymore. Where I am, if I'm going to think about Y being equal to little y, I need to be inside of the event X is equal to little x. Okay, so that's the new probability that Y is equal to little y. X equal to little x is now the new sample space. Similarly, if somebody tells me the value of Y, then I have a similar formula down here at the bottom of the slide. Okay, all right. Hopefully that kind of makes sense. Okay, moving on. So we also have this conditional mean, given that x is equal to little x, here we put mu of y given, and here we actually do use a little x. Okay, the notation gets a little bit cumbersome. And we write expectation of y, and we put a bar for given little x, okay? And then we use the conditional probability distribution for y. And we take all those probabilities and weight them, or we weight them against their y values, and that's our expected value. That's the formula for our expected value, okay? So that's a helpful little tidbit, okay? And these are a little bit grosser, but the idea is the same as things that we've seen before. I want the variance of y given x, then I need to look at the expected value of y minus the mean of y given that little x, which we have on the previous slide, squared, given little x, okay? Which means I'm going to add up all these things using the conditional probability density for y given x, okay? So that's where that formula comes from. There is a similar formula to what we have done before. Basically, everything translates over into the realm of not being in the whole sample space, but only on the event capital X is equal to little x now. So basically, I can just take the expectation of the random variable y squared given x minus expected value of y given x, that thing squared, that difference. Okay. Turns out that's going to be true just like it was before. Okay, so that's a nice little thing to bear in mind. Okay. All right. Let's look at this example. Now you may recognize this from before. This example should be familiar to us. This was the two-part quiz. X was the points earned on the first part of the quiz. Y was the points earned on the second part. And we had this joint probability density function or mass function. And what we want to do here is we want to condition on x's value. So we're going to say, well, I know that this student is going to get a 5 on the first part. Okay, that's just given. And so the first thing we're being asked to do is to find the conditional probability mass function, given that x is 5. And the second thing we're asked to do is to actually find the mean of this thing. Find the mean of this thing given that x is 5. Okay, so let's go do that together. Okay, here we go. So I've copied down this thing again. Remember from this table before, we had computed the marginal densities. That's gotten at by, okay, so like if I want the probability that x is 0, I need to add up all the various probabilities over all the y values. Similarly for, the marginal density for y, we need to add up all the x values, right? So that's how we got those things. Now remember, in this problem, we wanted to find the conditional density given that x is equal to 5. What that means is that we're going to concentrate on this row right here, okay? So we've kind of zoomed into the sample space right there, and we've zoomed into the sample space right there on the event that x is equal to 5. So we have those various probabilities, okay? And the formula says that what you want to do is compute the joint density, okay, at 5, 0, for instance. Okay, so y equals 0 at 5, 0. I see a 0.04, and I need to divide that by the probability of being in the new sample space, and that's 0.49. So 0.04, so for that first one, you would take 0.04 and you would divide it by 0.49. That would give us the conditional probability of being equal to 0. So that's the same thing as 4 over 49 if you think about it for a second. Okay. Now what about the next one? Well, that would be 15 over 49, and then 20 over 49, and then 10 over 49. Okay, so say 10. Okay, and of course, if I add all of those things together, I should get 1, and I do. They indeed add up to 49. Okay, so 19, 20 is 39, and then 10 is 49. So these do add up to 1, which is good for us. Okay, so there was the conditional distribution on the event where x is equal to 5. What about the conditional mean? What about the conditional mean? The mean of y given that x is 5. What would we do with that? Well, that's going to be the sum over all possible values, the sum of over all possible values of y, and I would use the conditional density, right? So this thing would be equal to, here I'm going to go up here, this thing would be equal to 0 times p sub y given x of 0, 5, okay, plus 5 times p y given x 5, or 5, sorry, this should not be a comma, it should be a given sign, right? So given 5, okay, plus 10 times the probability of y given x of 10 given 5, okay. We just keep writing that given 5 thing over and over. It's kind of annoying notation in some ways, but you know, we just do what we have to do here. Okay, so then it's 15 times p y given x of 15 given 5. Okay, so what do we get? Well, the 0 thing is obviously going to go away. And then I'm going to take 5 times, let's see, 5 times 15 over 49. Okay, so 5 times 15 over 49. Okay, 5 times 15 is 75. Okay, so it's going to be 75 over 49. Okay, I'm just going to write everything over 49 here. Okay, so 5 times 15 is 75. Okay, 10 times 20 is 200 when you think about it. And then 15 times 10 over 49, okay, is 150 over 49. All right, so what do we get here? Well, we get 350 plus 75 is 425 over 49. Okay, so 425 over 49. That is our mean. Okay? All right. Good stuff. Okay. We're out of time here, but let's just look at one other thing here. I want to talk about bivariate distributions of the continuous type, at least introduce this, and then we'll pause and we'll do some examples of this on Friday before we move on to other things. So we've been talking about bivariate distributions of the discrete type, so it makes sense that we would now want to move on to bivariate distributions of the continuous type. Okay. Here, one of the problems is we start having to do not just single integrals, but actually double integrals, because we have both an x and a y that are moving around. Okay, so x and y are continuous random variables. The joint probability density function, okay, we don't use p of xy for this, we use f of xy to remind us that this is a continuous function of, or you know, it's a, right, it's a function of continuous variables. The function itself doesn't necessarily have to be continuous. In fact, the graph of it is like a surface in three-dimensional space, hovering over the xy plane. Because for every input x and y, we get an output that kind of gives us a surface in three-dimensional space. Okay. So what about this density? What does it do? Well, it gives us the probabilities that x and y belong to some, two-dimensional set. Okay. So how do I get those probabilities? Well, I just double integrate over that two-dimensional set. the density, and that will give me the probabilities. Okay? It's really not all that different from what was going on in the discrete case. We weren't writing it down all the time, but it was really like a double sum. Like if I wanted, you know, I had P of X, Y, and if I wanted various probabilities for X and Y falling in some range, it was really like a double sum over X and Y. And here it's not surprising that in the continuous case, where we know we're going to have to use integrals, that you're going to end up having to do double integrals. Okay. So what does that double integral mean? That means I just have to let X and Y go over that whole set A to get the probability that X and Y belong to it. Okay, so that's kind of a picture of what's happening there. Okay, A is that shaded region, and the value of that double integral is really going to be the volume of that three-dimensional solid that's sitting right there in three-dimensional space. Okay. So X and Y move around in the base of that solid, and the density is that little surface on the top that kind of chops the thing off. And the probability ends up being the volume of that thing. Just like in the one variable case, we had area under the density curve. Okay, now it's the volume under the density surface, once again. But in the one variable case, the probability was the area under the density curve. In this case, the probabilities are volumes under the density surface. Okay, so the density is a surface now in three-dimensional space. What kinds of things would we need to be true about the bivariate density? Well, if I double integrate over all possible x's and y's, that is over the entire xy plane, I should get 1. And the density should never be negative. It should always be equal to or greater than 0. And how would I get the marginal densities for x and y individually? Well, I would just have to integrate out one of the variables. Just like before, I had to sum all of, like if I wanted the probability that x was equal to little x, and I had to sum over all the possible y values. Here I integrate over all the possible y values, and I integrate the marginal, or I integrate the joint density over all possible y values to get the marginal density for x. And similarly, I get the marginal density for y by integrating out the x variable. Okay, so those formulas are important. What does it mean for the continuous random variables x and y to be independent? Well, it means that if we go all the way down to the level of the density, the joint density, then the joint density at any x and y is equal to the product of the marginals. Okay? And that's just like what happened before with the joint probability mass function. Okay, the joint probability mass function. Okay, let me just remind you of that. I'll actually go back to it. Okay. Look at that. It's exactly the same, isn't it? Yeah, it's exactly the same. Okay, so let me just write something here. I mean, this is just the same thing as saying, because remember, let's kind of think about this for a minute. That's like saying, right, so P of x, y, that's just the probability that x is equal to little x and y is equal to little y. And what's the right-hand side saying? Well, the first thing is just the probability that x is little x. And the second thing is the probability that y is equal to little y. Okay? So it's not surprising that independence, because this is like, right, I mean, this looks like the probability of A and B is equal to the probability of A times the probability of B, okay? Which is exactly what we've come to know as independence, okay? That's one of the ways that we can phrase independence, if you will recall. So talking about the joint density function in the discrete case, and that being the determining factor for whether two random variables are independent, that makes sense, doesn't it? All we've done is we've just reframed what we know independence to mean in terms of the density function for the joint density function for these two random variables. And a similar thing is happening over here. A similar thing is happening over here. We're simply framing independence in terms of the density, right? The continuous density for each, or for the two variables. The joint density for the two had better be equal to the product of the marginals, and that will mean independence for x and y, okay? If that's not satisfied, then x and y are dependent. You have to go all the way down to the level of the density in order to determine whether two random variables are independent, okay? I think I'm going to stop right there. We'll start with some examples next time, but I just wanted to at least cast a vision for what we're going to do in the continuous case. We'll start with some examples next time. That's all for now.